Fiber optic transmission is the backbone of the modern internet. Unlike older copper wires, which move data using slow, heat-generating electrical pulses, fiber optics use light. At the heart of this technology are tiny, pure glass strands. These strands act as a waveguide, trapping pulses of light and carrying binary information across continents at near-light speed. Total internal reflection is the principle that allows light to travel through fiber optics. When light traveling through a material hits the boundary of a medium with a lower refractive index at a shallow angle, it is trapped. Inside the fiber core, the light acts as if it is hitting a perfect mirror. It continuously bounces off the cladding, staying confined within the glass wire over vast distances. This mechanism ensures that signals can be transmitted globally with minimal loss of intensity. A fiber optic strand consists of two primary layers. The innermost part is the core, a high-purity glass channel where light signals travel. Surrounding the core is the cladding. This outer layer is made of glass with a lower refractive index, which is the secret to keeping light trapped inside. Because the cladding has a different refractive index, it creates a boundary that forces light to reflect back into the core, a phenomenon known as total internal reflection. Fiber optic networks communicate using binary code. Data is translated into rapid pulses of light. A quick flash of light signifies a 1, while a period of darkness signifies a 0. These rapid pulses effectively turn light into a digital language, allowing computers across the globe to exchange complex information at the speed of light. The internet relies on a constant exchange between two different worlds, electricity and light. At the end of every fiber optic cable sits a transceiver. It acts as a specialized translator. Your computer communicates using electrical signals. These signals enter the transceiver, where they are converted into rapid pulses of light. This light travels through the fiber optic strand at incredibly high speeds. The transceiver's job is to ensure this translation happens near instantaneously. When data reaches its destination, another transceiver reverses the process, turning the light back into electrical signals your devices can understand. By bridging the gap between electrons and photons, transceivers make global, high-speed connectivity possible. A single fiber optic strand can only carry so much information on one wavelength. To scale capacity, we use wavelength division multiplexing, or WDM. Think of it as adding lanes to a highway. Instead of one signal, we send multiple distinct colors of light simultaneously down the same fiber. Each color acts as an independent data channel. This effectively multiplies our bandwidth without needing to lay new, expensive physical cables. By multiplexing these wavelengths, we transform a single path into a high-capacity superhighway for global data. Light travels at the universal constant, c, when moving through a vacuum. However, when light enters glass fiber, the density of the material slows it down significantly. In traditional glass fiber, light is impeded by the medium, traveling about 30% slower than in a vacuum. This physical limitation creates the speed gap between pure transmission and real-world infrastructure. The biggest leap in fiber optics by 2026 is hollow core fiber. In traditional glass fibers, light travels through solid silica, which slows it down. By removing the glass core and replacing it with an air-filled center, light travels significantly faster, nearing its true vacuum speed. This reduction in latency by microseconds per kilometer creates a massive advantage for high-frequency trading and AI data clusters. In 2026, every microsecond is a business opportunity. Whether for training massive AI models or high-frequency trading, signal speed is the ultimate competitive advantage. Standard glass fiber slows light down due to the refractive index of silica. However, new hollow core fiber uses an air-filled path, allowing light to travel closer to the vacuum speed of light. This technology shaves off 1.5 microseconds per kilometer. Over long distances, this creates a measurable edge that defines modern market leadership. For AI clusters and financial exchanges, this is not just engineering, it is the backbone of real-time processing. We are reaching the fundamental physical limit of data transmission in glass fiber, known as the nonlinear Shannon limit. Increasing signal power should theoretically allow for more data. However, in glass, high-intensity light triggers nonlinear effects. At these high intensities, the signal begins to distort, creating noise that corrupts the data. This is the nonlinear Shannon limit. Once we hit this limit, simply pumping more power into the fiber actually makes the signal worse, not better. This physical barrier is why we are now looking toward new architectures like space division multiplexing to multiply our capacity. Traditional single-core fiber is reaching its physical capacity, a bottleneck known as the nonlinear Shannon limit. To bypass this, we move to space division multiplexing, or SDM. Instead of sending all data through one central core, we use multi-core fibers. Think of this like upgrading a single-lane road to a multi-level highway. Within one cable jacket, these independent cores carry parallel data streams, effectively multiplying total bandwidth without needing to lay new, massive infrastructure. Modern data centers are facing a bottleneck in signal conversion. Silicon photonics solves this by integrating laser light sources directly onto silicon processor chips. Traditionally, electrical signals travel long distances to reach optical modules, causing heat and energy loss. Silicon photonics shrinks this distance, mounting lasers directly on the silicon die. By converting data into light at the chip surface, we eliminate the need for power-hungry electrical traces, significantly reducing heat and increasing data transfer efficiency. This integration represents the next leap in computing infrastructure, enabling the massive bandwidth required for artificial intelligence. Today's networks are no longer static. AI algorithms monitor traffic in real time across the global fiber backbone. By analyzing data patterns, AI dynamically reroutes light paths before congestion occurs, ensuring the most efficient data delivery. This predictive capability transforms fiber from a passive pipe into an intelligent, self-optimizing infrastructure essential for AI computing. Modern subsea cables are the silent highways supporting global AI. These cables connect continents, but legacy designs were rigid and difficult to upgrade. Today's infrastructure uses an open cable architecture. This allows tech companies to upgrade the transceivers and light equipment on land. By keeping the physical fiber static on the ocean floor, we can boost data capacity without the astronomical cost of replacing the entire undersea line. This flexibility is essential for AI, which demands constant bandwidth increases. Open cables ensure our global network stays ahead of compute requirements. Spectral efficiency defines how much data we can pack into a single light wavelength. By advancing our digital signal processing, or DSP, we are revolutionizing capacity. Historically, we relied on lower capacity streams, but modern DSP allows us to manipulate light waves with incredible precision. We rapidly scaled to 800 gigabits per second, significantly increasing the data density within the same bandwidth. Today, we are pushing the boundaries to 1.2 terabits per second on a single wavelength. This is the new standard for backbone infrastructure. By maximizing bits per symbol through advanced signal processing, we utilize every strand of fiber to its fullest potential, meeting the massive demands of global AI. Modern artificial intelligence requires unprecedented levels of coordination. Large compute clusters act like the brain of an AI system, but they must be connected by high-speed fiber optics to function. Fiber optic backbones allow thousands of processors to share information in perfect synchronization. Data travels as pulses of light at extreme speeds, minimizing the time needed for complex model training. Without this fiber infrastructure, the massive data throughput needed for today's generative models would simply not be possible. It is the vital nervous system of modern intelligence. Copper cables transmit data via electricity. Over distance, these signals experience attenuation or loss of strength and are highly susceptible to electromagnetic interference. In contrast, fiber optics transmit data as light pulses. Because light is not electromagnetic, it is immune to interference and carries signals over vast distances with minimal loss. External factors like power lines or lightning can disrupt copper signals, requiring frequent boosters. Fiber, however, maintains total internal reflection, ensuring data integrity across continents. In high-frequency trading, proximity to the market is everything. Financial hubs like Chicago and New York have upgraded to hollow-core fiber backbones to gain a crucial edge. In standard glass fiber, light is slowed by the silica material. Hollow-core fiber, however, uses an air-filled tunnel, allowing light to travel closer to the vacuum speed of light. By saving just a few microseconds per kilometer, trading firms shave significant time off their transaction latency. In this industry, those nanoseconds are worth millions of dollars. As of mid-2026, the optical communication market has reached a valuation of over $35 billion. This surge is driven almost entirely by the relentless bandwidth requirements of modern AI models and massive hyperscale data centers. As computational power scales, the infrastructure connecting these server clusters must expand to keep up with the data flow. Today, fiber optic technology is no longer just a utility. It is the fundamental infrastructure enabling the AI revolution. Standard single-core fiber is reaching its physical limits. As data demand explodes, we are hitting the nonlinear Shannon limit, where adding more light power no longer increases capacity. The solution is the multi-core era. By integrating several independent cores into a single cladding, we multiply capacity without laying new infrastructure. In this architecture, light pulses travel in parallel through different channels. This enables metropolitan backbones to scale exponentially to meet global traffic demands over the next 5 years. The history of fiber optics began with simple lit fiber, serving as a static bridge for data transmission. We have transitioned into an era of AI-managed, programmable photonic highways, where light itself is actively routed and optimized in real time. Ultimately, the future of the internet is defined by how effectively we can manipulate light, turning the fiber backbone into a living component of AI infrastructure.